Hello, everyone. We are part of the Clean Energy Corps here at UMass. Our team is comprised of Manav, Lexi, Brett, and my name is Jake. We study both the building science and the construction technology, and we work with communities across Massachusetts to help improve the efficiency of their facilities and transition to clean energy. Today, we're here to talk a bit about the Medfield State Hospital and the application of a district energy system. We'll cover what they are, how they work, and how this type of system could benefit the Medfield State Hospital project.
Some background on Medfield State Hospital. These are the buildings we're working with that sit on a 128-acre piece of land. It was established as an insane asylum in 1892, and then it became designated as mental hospital in 1914. It had agricultural fields as well as dairy farms, hay fields that grew onions, radishes, sweet corn, lettuce, beets, carrots, you name it, they had it. The head farmer actually studied animal husbandry at the Stockbridge School of Agriculture at UMass Amherst in the 60s. And then in 2003, the Mass DEP assessed the hospital and came to the conclusion that the air quality was poor due to the fact that it had too much asbestos and too much lead particulate. So it closed and the town of Medfield bought it in 2014. Currently, it's being used by walkers and joggers daily. This land has always had great potential to be something magnificent. As it stands right now, it's not overgrown and completely abandoned, but the whole campus will need new utilities. The hospital was originally heated with a steam district energy system. Finally, it's a historic site with beautiful architecture. And because it is registered on the National Registry of Historic Places, there are some constraints for exterior facades, windows, doors, etc. This is a great space, and we want to preserve the beautiful aesthetics of this campus.
There are no on-site utilities, which means it needs water, it needs power, it needs sewage. This presents an opportunity to design and develop a utility system with clean energy in mind. There is a gas line nearby, but it would be possible to save money by not extending the gas line and instead investing that money in clean and renewable energy systems. One thing we'll be referencing later on is heating and cooling using geo-exchange, which would enable the site to be entirely heated, cooled, and powered by renewable electricity and purchased from the grid or produced on site.
So some of the town goals for the site redevelopment. The town of Medfield is looking to redevelop this campus into a community consisting of senior housing, affordable housing, and commercial shops, such as restaurants and art centers. We looked into what Medfield wants for this project. In Article 20, the Medfield State Hospital District Zoning Amendment, it outlines in the purposes of Section 1, subsections F and G. They say that F encourages preservation and rehabilitation of historic buildings, and G states that we encourage the adoption of energy and water efficient building practices and sustainable construction methods and practices. We have designed our solution to fit this exact criteria. Our solution is that we are proposing a district energy system, as it will address a number of the site's needs. It would allow for all of the energy efficient heating and cooling systems while keeping the site's beautiful aesthetic and historic feel.
So your next question might be, what is a district energy system? A district energy system is a system that uses centralized equipment to transport heat energy to heat and cool buildings. A DE system circulates low temperature hot water or cold water for climate control of the interior space. It can also provide or preheat domestic hot water. Using low temperature hot water around 90 to 120 degrees Fahrenheit not only reduces energy loss, but enables a higher efficiency in the provision of heating and cooling, and allows a wider range of potential energy sources. It's made up of three basic sections: the heating and cooling plant, the insulated underground piping, and then the buildings. The first section is the heating and cooling plant, where water is both heated and cooled. From here, it's moved to the pipes. The second section, the insulated underground pipes, move the heated or cooled water to the buildings. The transfer of heat between the buildings and the pipes is used to control the temperature inside the buildings. Hot water will bring heat to the buildings, while cold water is used to absorb excess heat from the buildings where there's a cooling demand, like in the summer. The third section is comprised of the buildings that are connected to the system. How does the system work? The graphic seen here shows the evolution of district energy systems since the early ones in the late 1800s. The first generation was a very basic system that focused on recapturing heat created while burning fossil fuels to satisfy the demand for energy production. A modern district energy system may use natural gas instead of coal, and more efficient systems are completely electric based with renewables. Modern systems are highly effective at recapturing heat energy that's normally lost, as well as reducing energy demand. The versatility of these types of systems lends them to be easily integrated with any of the renewable technologies shown in this graphic. On this graphic, you may also notice that there are red and blue lines at the top. The blue line represents the average efficiency of the DE system, and the red line represents the average temperature of the hot water being delivered to the buildings. They tell us that circulating lower temperature hot water enables higher efficiency of the system, reducing energy wasted when heating the building. Lower temperatures reduce the amount of heat loss that happens during transmission. The lower the water temperature for heating, the higher the efficiency the system can have. Below 60 degrees Celsius, which is 140 degrees Fahrenheit, it's possible to use renewable energy and heat pumps to deliver heating at efficiencies as high as 800%. There are several modern DES characteristics that Medfield would benefit from if included in the design, such as designing for prefabricated distribution systems with accurate metering, designing for multiple sources of energy. You'll notice that the fourth generation of DE systems can make use of both short and long-term heat storage, geothermal energy, and centralized heat pumps and chillers. Designing for low energy buildings, effectively allowing the DES to satisfy all energy needs at considerably lower cost to an individual, at considerably lower cost than individual systems in each building would. We will be discussing high performance standards for insulation and air sealing as a critical recommendation in this section. Lastly, designing for two-way district heating and cooling, allowing the system to trade heat between buildings. This means buildings with excess heat have it removed and transported to buildings that need heat, resulting in an extremely high efficiency. I also want to point out that being part of a district energy system does not mean that every building, every section within each building gets one temperature. There are thermostats in each of those areas to separate heating zones, and residents in each unit can choose the temperature they want, and the temperature sensors end up sending heat to where it's desired. So these systems are great, but where are they already in use? Well, there's over 700 throughout the United States, including several in our region. To name a few, the city of Boston and the city of Cambridge, UMass Amherst, New York University, Princeton, and anywhere in these cities, these 45 cities around the world, which includes Europe, where DE systems are even more common. A DE system allows for easy expansion for other sources post-development of the DES. This is really important. Like a solar field could be readily integrated into the energy system without any major overhaul. A thermal storage field could be added. Hygienic heat recovery from sewage could be added, and emergency backup generators, which should be added. DES can be easily managed through various systems, such as a Geographical Information System Network, known as GIS. And GIS is a spatial data tool, which Brett will go more in depth on right now.
So as you can see with district energy systems, there is a lot of potential, a lot of things you can do with it. So we'd want to recommend it to be managed as effectively and efficiently as possible. GIS, Geographical Information Systems, would be the best way to do this. GIS is a spatial data tool, platform architecture, database, and various other things. GIS, it can store the building data information accurately and model and display these sort of energy labels, as you can see from the graphic on the right, so you can help dedicate where energy direction will be needed, especially on a site that has varying building development years and efficiencies, with an added factor of also hosting building infrastructure and anything else that can relate to the DES. With pipe planning as well as an extension, GIS can generate the most efficient and cost-effective routes for these pipelines, such as going through a grassy field or area instead of intersecting under various building structures that have pre-existing pipelines, so it can keep future planning consistent as well as lowering further costs. And it can also help with documenting workflows and automating those with the added benefit of increased consistency to pinpoint these issues and maintain work orders.
This DE system we propose comes with numerous benefits, such as it allows for cheaper operational costs, efficient energy production, and heat recovery. It's future-proof, as mentioned before, meaning there's flexibility with renewable energy and reduced maintenance costs. There's also benefits that haven't been mentioned yet. These buildings were designed for using a district energy system application, as Jake mentioned previously. This hydronic heated water distribution system uses small pipes as opposed to large air ducts. Retrofitting is a difficult process that doesn't give the best results. It would not apply to this project because this system could be designed specifically for this Medfield State Hospital. Avoiding retrofitting avoids one of the largest costs by doing it right the first time. District energy systems are not restrictive, just as long as the developer designs for low temperature hot water. Finally, a DES allows for easy expansion for other energy sources post-development, as Jake mentioned previously, as well as easily manageable through various systems like Brett also mentioned. But while there are many advantages, every system comes with some challenges. There is a large initial investment into infrastructure, materials for piping, engineering, planning, time. This is not a small piece of technology. This picture to the right illustrates the typical size of a district energy system in an urban business district. The blue and red lines represent the underground insulated piping. Finally, the DE systems are more common in Europe than in North America. So many local developers may not have built a DE system before, but that shouldn't be excluded solely on that. We will recommend the developer qualifications later in our presentation.
Our team agrees that as part of the DES, a geo-exchange field combined with heat pumps should be a part of the system. Let me share a bit about those. Heat pumps are powered by electricity, and heat pumps aren't just for heat, but can provide both heating and cooling. They operate similarly to a traditional air conditioner, but can switch between heating and cooling modes depending on the season. In the case of district energy systems, they can also move heat from a building that requires cooling to one that requires heating, essentially doubling the energy efficiency. Heat pumps move heat across a temperature gradient rather than generating heat from combustion of fossil fuels. This improves the system efficiency. And heat pumps can use a variety of heat sources and distribution systems, which we'll discuss more in detail on upcoming slides. Heating and cooling can be distributed in the form of hot and cold water, a hydronic system, or air.
There are a variety of types of heat pumps, and this slide gives an overview broken down by heat source, which is where the heat pump obtains heat in the winter for heating purposes and where it rejects heat in the summer for cooling purposes. The first option is an air source heat pump. They are most commonly used in the US, and they have the lowest initial cost. Their heating efficiency and capacity does decrease with decreasing outdoor temperatures, but even in very cold weather, modern heat pumps still provide heating at twice the efficiency of boilers and furnaces. Another recommendation we ask you to consider is a geo-exchange system, also known as a ground source heat pump. These use underground piping as the heat source, which requires a greater initial investment into infrastructure, but also provides higher efficiency because the temperature underground is more consistent throughout the year. Geo-exchange systems require appropriate site conditions, which Brett has created a suitable map and will discuss shortly. The last option you should consider for this site is a water source heat pump. With this, the nearby Charles River could be used as the heat source.
Okay, so you've heard us discuss geo-exchange a few times by now, and with that being one of the main energy sources, we want to dive into a little more detail here. So at its simplest form, geo-exchange is a form of thermal heat storage where that heat can be stored and reused in the future. A geo-exchange field works by drawing its power or the heat from one source and then pumping it into the other. So in the winter months, that heat would be drawn from the earth and be pumped back into the interior spaces of the buildings. In the summer, that heat will be drawn out from the buildings, those interior spaces, and then pumped back into the earth to be stored to be used at a later date. So it's different from typical space conditioning units where geo-exchange heat pumps, they're not exposed and they'll have fewer mechanical parts working. So it'll be much easier to find a source and central location. You have better visibility and ease of maintenance there. This is what you call a balanced heat source and heat sink. They're much more dependable due to the earth having a very consistent temperature as opposed to outside air temperature used in many heating systems, which is a high amount of fluctuation to it. And with these geo-exchange fields, you can't really simply put them in any single field. You'd want to do it to maximize its efficiency. You'll hear us talk about maximizing efficiencies many times. So geo-exchange fields, they have these certain conditions of where they should be implemented based on a variety of factors. One of those big factors is going to be dependent on the soil. There are various soil characteristics which can make geo-exchange far more efficient and suitable. Some of those being proximity to the water table, how resistant that soil is to flooding, the moisture content, and then the soil saturation and drainage of that. So here we have a map of every soil located on the Medfield State Hospital campus-owned land as taken from the Strategic Reuse Master Plan. Each soil is reported from the U.S. Web Soil Survey, and that includes various attributes and characteristics that will be helpful in our planning and analysis. Here is one of the examples of how GIS is actually used to analyze site suitability and to help plan the location of this geo-exchange field. So the soils that are in the campus area were rated on a 3-point scale for how suitable that makes it for geo-exchange. Each of the soils displayed in the previous slide contain these attributes that we take a look at here, and there's a heavy correlation between geo-exchange suitability and overall development for further district energy system expansion, which we'll also talk about a bit later. So here is the overall result of what we looked at for our site suitability here. The scale shows more suitable locations in this darker red color. And we advise that based on this analysis that we start looking towards the north fields as it's one of the most suitable locations that's available, as a great amount of surface area, easy to dodge the forested areas, there's potential for diagonal bore fields, and as a great physical location being that it's off of the campus area, not directly integrated inside of it, but it's also not too far away to have convenient pipeline routing. And you've also heard us talk about many possibilities for future-proofing and expansion beyond just geo-exchange. So these DE systems are very versatile. They can utilize a variety of energy sources. There are several options just beyond geo-exchange here. Eventually, development and associated heating and cooling energy demands may expand beyond the capacity of the available land. So utilizing the Charles River actually has potential for an unbalanced water heat exchange. This can complement the balanced heat exchange provided by the geo-exchange field. There's also heat recovery from sewage. You have most water headed down the drain that's heated from anywhere from 90 to 110 degrees Fahrenheit. It'll travel through the pipe. It'll be used very shortly for just about a few seconds, and then it goes right down the drain and the energy is lost to the ground. What we aim to do with this district energy system is recover that heat, well, not reusing the water, which is now classified as sewage, and has a huge potential to give the Medfield State Hospital massive energy savings. Unlike geo-exchange, which uses the thermal mass of the earth relatively close to the surface to extract and deposit heat, you have the potential for deep geothermal, which is a cutting-edge technology. It's enabled by new drilling techniques that directly harvest the limitless heat of the earth, more than a mile below the surface, even areas like ours with low seismic activity. This technology is in development, but it's very promising, and it's entirely compatible with the existing district energy system. One potential land use for some parts of the property might also be a solar voltaic array. The electricity generated could partially run the DES. However, another solar application would be to collect solar thermal energy and store it either in a large thermal storage tank or directly inject that heat into the geo-exchange field during the summer, because you would therefore increase its heating capacity in the winter. Large solar thermal DES systems have been operating for more than a decade in places like Canada and Denmark as well. Solar thermal in particular can be especially utilized when it's close to the grid, as it would be in this case with DES here. One option by injecting that into the geo-exchange field is just keeps it at its peak efficiency as far as you can. So the main theme we want to reiterate here is just how this district energy system can open up many, many doors, give you many, many options leading into the future.
As you can see from the graphic, all of the heat sources we discussed operate at a relatively low temperature for a heating system. And using a low temperature hot water system, we can effectively use those temperatures provided in the most efficient way. Heat loss is a pretty big factor in most systems, and more heat is lost when the temperature gradient is larger, meaning having a low temperature system means less heat is lost. Little hot water pipes are better than large air ducts at transporting heat as well for the same reason. By using heat in the most efficient way, we can save on energy costs since heating is usually a big contributor of total energy use, and we can use hydronic systems to distribute this low temperature heat to indoor sources. So low temperature hot water systems have a variety of inputs and outputs for both heating, like radiant flooring, ceiling and floor panels, and wall radiators, as well as cooling, like fan coil cooling and ducted hydro air systems. We can also use radiant flooring as cooling. When renovating a construction, it's important to consider the future life of the building. High performance envelopes are crucial to maintaining the building characteristics long into the future. And the passive house standard is a high performance standard for that metric. It offers high levels of insulation, energy recovery systems like heat recovery ventilators or HRVs, and minimal heating and cooling required. Aiming for passive house levels of building performance is better for the longevity and sustainability of the site. There are some historic restrictions, however, mostly relating to the NPS regulations, like maintenance of historic character, complying with building code, or better if possible, and sustainability goals. However, there are no need for compromises since using the site's available well-designed resources, as well as modern construction techniques, it lends itself to creating a historically pleasing building with all of the benefits of high performance as well. One good example is a survival of the brick detailing. It means that it was designed with the future in mind, and we're able to figure out from having no interior heating that the brick will be able to handle the future insulation as well, since the heating and cooling it would have experienced already is enough to know it can handle internal heat shifting as well. Also, if you note that the brick detailing at the roof level is designed to shed water away from the building's envelope to protect that brick from moisture damage. Some extra measures might need to be taken at the window and ground joints, however. The ground may need to have some more drainage to protect the ground level brick from future moisture damage. We can't tell exactly, but it's usually good practice. And you can tell that the windows are kind of leaky in masonry, but you can see in the windowsills that it's actually leaking out of the windows. So it's shedding water away from the interior, which is a good sign of brick construction. The picture to the left here is of an original historic window, and the far right window is a passive house certified one. It's important to note that they look just about identical, even though they provide vastly different utility to the building envelope. The infrared picture in the center is good to show that there's a notable difference between the passive house windows heat transfer rate in the center and the original historic brownstone windows surrounding it. These passive house windows are available from multiple vendors as well. So historic windows do tend to be quite historic buildings do tend to be quite thermally inefficient since they weren't constructed with our current understanding of insulation in mind. Companies have products with historic looks that can be used to remedy this exact case. These companies focus mainly on historic retrofits and as such have a myriad of products for any number of use cases, and using them in a whole site redevelopment means we get the efficiency of a modern envelope without having to sacrifice the historic look. Using the existing materials on the site increases the embodied carbon of the development, lowering how much carbon is used during the build process, also again aiming to maintain the same look and feel. Upgrading the building's envelope increases the efficiency of the whole site, like I said, since buildings take up a large portion of energy usage. And having such a deep renovation means we can install foundational insulation as well as radiant flooring while installing drainage or other ground level infrastructure. It all boils down to maintaining the feel of the site while modifying the envelope of the buildings to increase the total efficiencies.
Now, diving deep into specifics related towards the town of Medfield, it is important to note that once the property is sold, Medfield has very little control over the choices the developer makes. So developer selection and early standard setting is critical to success in meeting town goals. To ensure that the goal for a high site reuse value is met, we recommend that Medfield uses a variety of approaches at the point of maximum leverage to make sure that the main goals are met for historic preservation, energy efficiency, minimized carbon emissions, cultural, business, and residential development. Existing ordinances require compliance with historical commission guidelines. We have illustrated several ways that this does not have to act as a barrier for high performance buildings. On the contrary, very high performance windows with historically appropriate appearances are still available. There is no need to compromise by allowing combustion exhaust and outdoor HVAC units if all heating and cooling is connected to the DES piping system hidden underground. Also, the town may want to consider enabling ordinances that allow the existence of management of a DES by a third party, and may similarly set minimum standards assuring that all development on the property is capable of being connected to the district energy system. It may be preferable to use a bid adder in selecting the site developer that gives credit for the plans with DES compatible HVAC and passive house level building and envelopes. Most building permit requirements are constrained by Massachusetts stretch code, but special permits and benefits are offered, like awarding the town the ability to develop specific non-developable land. We recommend applying requirements for very low heating energy demand. Methods include using passive house standards or simply requiring a maximum heating.
We don't want to recommend any specific developers, but we feel they should have at least these characteristics, since if the developer isn't able to use the site most efficiently, the true potential of the whole site redevelopment may not be utilized. Choosing an ideal developer right now may prevent complications and expenditures in the future.
So here's a summary of what we've discussed and what we want the main takeaways to be. Medfield has a golden opportunity with this site. Because it has no utilities, we can put in high efficiency utilities that align with long-term energy goals. Implementing a DES fits with zoning requirements already established by Medfield. A DES designed for utilizing heat pumps allows for higher efficiency and lower peak demands. To enable the use of heat pumps and heat recovery, designing for low temperature hot water is critical. As Brett mentioned, a GIS helped us define and create a suitability map and would help the system manage the energy usage. Here to minimize building heating loads will reduce the required size of the geo-exchange field, keeping the geo-exchange field confined to the most suitable areas and minimizing capital costs. As Manav covered, these buildings are both historically significant and still viable. They've been standing for more than 100 years, and making the correct investments would keep them standing for 100 more. Designing low-load buildings allow for low-temp hydronics, which enables highly efficient, high-performance, low-cost buildings that receive energy from multiple sources. If the buildings are designed for high efficiency, the entire district energy system will perform at high efficiency and benefit from efficiencies of scale, which can reduce both overall capital costs and operating costs.
On behalf of my team and I, we would like to thank you all for taking time out of your day to be here for our presentation. We hope this information was helpful. If there are any questions or concerns, please feel free to ask now.
Why don't we
Ben,
unshare
good.
and unshare the screen and open up for questions or comments.
Well, from the Medfield Energy Committee, let me be representing them. Let me thank Jake, Breck, Lexi, Manav, and for an excellent presentation and really well done. Very impressive. And Lauren and Ben, thank you for all the guidance that you've been providing. I see that Fred Davis is on, so I have taken over his role. So I will turn it over to him, but I just did want to let you know from an Eversource perspective, also putting on my other hat, I thought it was very, very well thought through about leveraging district systems and on the challenges and solutions associated with retrofitting these older buildings to this net zero standard. So thank you very much. Well done.
Penny, thanks for that. This is Fred Davis. I'm chair of Medfield Energy Committee. I thank the unit introduced a number of elements that are needed in this discussion. We have the Energy Committee, as part of the Energy Committee, to get us to this far, and particularly George Whiting. I also want to thank two people on the state level that I know are on this call. Thank you for being here, and that's Kelly Brown and Joanne Becerra, and perhaps there are others. And I do want to make sure that particular questions do come up. So, but I want to make sure to get those thanks and appreciations and applause. It's hard to do on a Zoom call, but applause from all of us. Thank you.
Well, as another member of the Energy Committee, and in fact, I lead the subgroup that's been working on the hospital property. This is a great compilation of a lot of things that we've talked about with the Development Committee that are our hopes and aspirations, but I think you packaged it in a way that is really, really helpful to see how these different strategies and these different approaches are not one-off things you do here or there, but if you think through it very systematically, you can really capture the maximum amount of benefit. I do have a couple of specific follow-up questions, unless somebody else wants to jump in here. Hearing
You're
none,
the best to lead this.
Hearing none, I will jump in on a comment early in the presentation. You talked about the, since there are no utilities on the site, the efficiencies of co-locating the infrastructure as it's designed and installed. Could you elaborate a little bit further on what goes into thinking about that and how that could play out here?
Which one of us wants to take this question?
Jake, do you want to take a first shot at, and I'll fill in if needed?
Yeah. Okay. So by putting in all utilities, you can choose utilities that are compatible with each other and design in a way that works efficiently. Ben, I think I have to hand it off to you.
All right. Well, I'll hand this one. It is complicated. Yeah. So there are a bunch of things, again, that if you build it once, you don't have to build it again later. The kind of the most obvious one to me is that if you're putting in new sewage pipes, you can actually purchase preformed sewage pipes with integrated stainless steel exchangers, so that you can do all your heat recovery from the sewage without any of the complications of building a secondary heat exchanger and the cleaning and all the things that have to deal with that. In this case, it's simply stainless steel exchangers on the underside. And this is actually fairly common in some new development, mostly in Germany right now, but this one where you do it once, you're already paying for the biggest part of all of this is excavation, right? That's going to be the biggest cost. So if you can do your excavation once and line up all your utilities and put them neatly where you need them to be, you've saved on the expense of having one service do its excavation to one depth and another service do its excavation to another depth. You plan it together, it's all laid in once, you get a big upfront cost savings. And again, where you've got these interactions of temperature resources, that's kind of the big one. And similarly, if you're dealing with water and insulation, and then electrical wires, which in this case you might bury in conduit, you can have the things in their appropriate depths. You can build access. Back in the original situation, you would have had, or you do have, steam tunnels, but they're kind of small. And one of the challenges is if you're moving to move the same amount of energy with water, you actually need a slightly larger pipe, because you're going to be because you have less energy per volume of material. And so you have to, that adjusted by the speed of the pumping, et cetera. But so you're going to tend to not be able to reuse the same tunnels, but by putting them in kind of an organized way, again, you've saved money on the excavation and the organization, and allow, for instance, one of the things that makes a DE system work well that Brett alluded to is essentially metering and sensors. And so if you have temperature sensors and meters kind of well distributed through the system, you can actually fine tune where things are going to go. It also makes it more retrofittable if you're not simply burying a piece of pipe underground and then you got to dig it up. So those are all the sorts of things where they can combine.
Got it. Great. Great. I mean, it sounds like, I certainly thought, the idea of, dig once and bury everything together. Agreed. Yeah, excavation is expensive. So I certainly anticipated that was one savings, but you're alluding to kind of future proofing and ease of maintenance and upgradability, which I hadn't thought of. And I think that is, a really, really interesting advantage of that. My second question has to do with the buildings. And, thank you for your, sensitivity to and attention to the historic nature of those buildings, which is very important to the town. I wanted to follow up on your comments about the brick and how the brick has withstood the test of time, particularly over the last 20 years without any heat in the buildings. Because that is very tricky, I know, in masonry construction, particularly in brick, that if you over insulate, depending on the characteristics of the brick itself, you can create, problems. I think you alluded to like some additional testing or something of the brick, but the fact that there hasn't been a lot of damage to the brick in the winter when it would absorb water and then freeze, indicates that it's a pretty high quality brick. But what else would be needed to sort of confirm that brick characteristics, and how would that then help inform the insulation strategies when they start rehabbing the buildings?
Manav, do you want to take a shot at this, and then I'll fill in?
So like kind of on that idea, I don't know if you remembered, but the brick detailing on the roof was able to shed water away from the brick, which means that moisture wasn't a huge issue for the brick's like lifetime. There is some testing we can do to like figure out what kind of insulation and stuff we need, but it does look pretty good all around. But yeah, Ben, you know a lot more about.
Yeah. Well, I'll just kind of explain kind of the concept here, and we have a big history, especially back in the 1980s, of people insulating brick buildings, and all of a sudden these buildings that were solid brick masonry, structural masonry, and all of a sudden they start spalling, falling apart, and so this fear is a justified fear. But it really comes from two different damage functions, both having to do with water. So one is on the exterior of the building, where bricks are very hygroscopic. They can absorb a whole lot of water. So in one, say, rainy period, they're going to get a lot of water on them. And then if you imagine a situation where that brick freezes, then you get damage functions. We see no damage. And so this damage function, the exterior damage function, is a result that you would see if you took a building that was uninsulated and made it very, very well insulated, is the same as a building that's been unheated for whatever it was, 10 years or so. So that gives me a lot of confidence. And if you look again at the details Manav was pointing out, all the dentils that run up and down, it's actually classic drainage. People should build buildings like this now. They got all the details right, and so it drops the water off. And in fact, if you look at those windows where you see the little white streaks, those are probably paint runoff from the white paint that was on those windows, which may have lead and God knows what. But But if you look at where it goes straight down the front. It doesn't go around into the corner. And that's an indicator that there are already back dams and kerf cuts designed into these very well-designed windowsills. So in other words, the system is well-designed for exterior damage function. The next thing you have to worry about is an interior damage function. Water that where the source of the water is from the interior. That water source is going to be, well, you know, if there's moisture in the building of some source, but the biggest source is humans breathing, right? That's our biggest source of water. And here, the reason you would get damage function is that you move water from a high concentration in the air across to the outside, right? And so it's got this vapor drive, and then you hit a condensing surface, which in this case would be the interior wall of the brick. The brick is able to absorb a lot of water, and what you could end up having, and did happen a lot, again, mostly in the 80s and 90s, was spalling and freeze thaw effect of the brick on the interior, where you don't see it until it's way too late. The way to prevent this is what was, so Manav showed you one example of many possible engineered examples. This example comes from a company called 475 that specializes in passive house materials. And they tend to avoid spray foam. Quite frankly, spray foam is a really simple solution to avoid this problem entirely, but both systems work. And the idea is to have a vapor closed system with on the interior of the thermal insulation that's also a perfect air barrier. However, you also want the ability to dry to the interior. And so these newer systems use a smart membrane that adjusts its vapor permeability depending on the overall relative humidity on either side. So the basic point is that the new techniques, rather than saying, let us only do it if the brick is good and then take risks, it says, let us engineer a system that can protect even a questionable brick from the interior by designing that system to resolve. So that's kind of been done. The final answer is you would still want a company to do what's called a Woofie analysis. Woofie is an acronym for something German. I can't remember what it is, but it does an hourly analysis over many simulated years of what would happen with different assemblies. And so that will give you kind of your highest level of confidence. Pretty much any passive house certified contractor, so someone who's doing passive house certification, will do Woofie analysis as part of their service.
Would ventilation also play a role in that control? Because in passive house, you typically are bringing in a controlled ventilation, so that would probably help balance some of that humidity and stuff as well, right?
Ventilation is going to be critical to any of these. So we're going to assume that anyone who meets stretch code is going to have to provide ventilation of some sort. Anyone who designs to a passive house standard is going to have to provide not just adequate ventilation, but well-distributed ventilation and using a high level of heat recovery. Yeah. So, but either way, you're getting ventilation. And I would say the overall HVAC system will be designed to maintain humidity levels within a kind of normal band.
Yeah. Yeah. Okay. One last question, and this is a big one. So I do the best you can with it, because I think there's a lot of unknowns here. But certainly from the Medfield Energy Committee standpoint, the idea of not bringing in gas lines and avoiding having fossil fuel on the property is something, we're very much in favor of. But, from the town standpoint, of course, there's the reality of, getting the property developed so it's economically feasible, for the developers, so that it is, attractive to potential residents and things. So, it comes down, to some extent in terms of cost. And the difference between the costs of bringing in the gas line and then, installing all the distribution across the campus of gas versus the installation of the district heating system and things like that. Any sense of relative costs, or again, some of these other examples and sites that you talked about? Any sense of cost from some of that?
I'm going to answer this. Sorry, guys. I'm just going to take this one.
I know it's a toughie.
And
So-
I'm going to say that this is not the right way to think about the question, because what you need to do is think about the life cycle of the project. Now, if you're a developer who wants to get in and out, you are looking at how can I have my lowest first costs? But if you are the town of Medfield, you want to consider, what will we do with the stranded asset of all this natural gas equipment? And what will we do now that we have to retrofit all of these buildings in 10 years? Now, I'm making an assumption that the climate commitment that the state of Massachusetts just signed, right, that is now law, goes into effect. If that happens, natural gas is on its way out, right? There is simply no way to meet the climate commitment while continuing to burn natural gas. And therefore, either there has to be a price, some sort of carbon price, or there has to be some regulation. Something has to happen. I mean, it could be that we just don't comply with our own law, but this is now projecting into the future, what will happen. But this approach is future-proofed. So I would say that the cost of laying pipelines, the cost of dealing with a dangerous substance that requires maintenance of pressure, right, and the substation involved with that, versus the application of water and pre-insulated lines. Most of those cost factors are very similar, right? Minus the the added expense to deal with gas, but it's the 5 years, 10 years down the road cost factor of retrofitting things and dealing with this stranded asset. So where you've paid for it, and if you're a utility, which it depends on how it's funded, right? You have an asset that you are depending on for your rate, right? So that's, I think, is the better way to think about it, is essentially what happens to the town of Medfield when it has a new development that all of a sudden needs to be redeveloped again, and could you avoid that cost? So I think life cycle costing really is, and I'm not talking about life cycle assessment, we're looking at carbon emissions, but just life cycle costing is complex, and that's why I'm not giving you a simple answer. Oh yeah,
Right.
X is cheaper and Y is cheaper. Overall, the equipment cost, if you add up all of those furnaces, imagine you took every single one of these buildings, you ran a gas line to each one, and you installed an appropriate boiler or furnace, and you installed some sort of air conditioning unit, and the historical commission says, yes, it's fine, we're going to have all of these exterior appurtenances showing up. Then let's imagine a situation where there's no gas. Now you've designed a distribution system that's incompatible with low temperature hot water, unless you did the otherwise. And so you have to actually rip out a bunch of your equipment and put in new equipment. So the life cycle cost of that decision becomes very, very large. But yeah, in the end, it comes down to your prediction about the future and whether you believe we as a society are actually going to do what we seem to be inclined to start doing, maybe, but have mostly failed to even try to do up till now.
Yeah.
I have a comment and a question. First of all, thank you very much for this fantastic presentation. And it's very, very broad, and you got into some very good detail, and I'm very impressed with what you guys came up with. So thank you for that, and I hope that you all get to come to Medfield sometime and take a look at the site and tour it. Maybe there'll be some interesting DE system there in the future. But my question would be, a developer might come in looking at a site and thinking, we want to develop this, but it might take some time. We don't want to have a district energy system. We don't want to size a district energy system maybe, or it might be very expensive to create something for this huge campus and all these buildings, rehabilitated buildings and new buildings. Is there a way that you could accommodate a slower rollout of a development?
But the students had the project of
so we actually did have some discussion about phasing, which is essentially what this is about.
Right.
So I think the students' main takeaways still apply. In other words, let's say you're developing only one of the buildings and the other ones you're waiting on, and it makes sense to let's say it makes sense to bring natural gas to that one building without having to do the extensive natural gas network to the whole rest of the development. It might make sense to say, okay, we're going to develop this one building. We're going to install condensing natural gas boilers and some sort of air source heat pump or air to water heat pump, whatever, depending on the building and the size and the use and all those sorts of things. But you design it as a single building as opposed to a whole development, which is what you're doing. But if you design it with a high efficiency envelope, then later on, you're still compatible with a district energy system or any other heat and cooling source. If you design it with low temperature hot water heat emitters or compatible heating and cooling systems, then you're compatible with the existing system that you brought in that you intend to throw away eventually or use as backup. The other thing is, and this is a perfectly valid phasing approach, is you start with one building and you build that power plant such that it can be the heat source connected to a district energy system that you build out as you extend sewer lines and water lines and electric lines to the next one. You actually simply continue to upgrade or upsize the power plant or the heating plant and cooling plant that you put in that first building, which then avoids at least running gas lines to the rest of the place. And so you basically build out your DE system from there until it, that's the nice thing about these systems, is that they go in multiple directions. So eventually you say, okay, it's now big enough, we need to build a geo-exchange field, or it's now, we've now had time to simultaneously develop the arts center and the senior living center. And now it makes sense to develop the first part of our geo-exchange field and install more geo-exchange as it goes. And then, upgrade your building. So to that extent, almost all of these district energy systems start small and grow, usually in a planned way.
Yeah, and I would just like to add on that as you think about it, we are going to do 3 pallets of geothermal systems over the next 3 years at Eversource. So you give time for that to mature. I also believe, Ben, that would allow for, if you wanted to use the natural gas as a backup generation source in a situation of needing that resiliency, it would give you that flexibility. So it is something to consider from a phasing perspective and a resiliency perspective. I've got to drop off, but this has been really, really good. Thank you so much. Excellent presentation.
Thank you very much.
Take care.
I'll need to drop shortly too. This is Todd Trebanco from the Medfield State Hospital Development Committee. I wanted to thank the team for the invitation and the very interesting presentation this morning. We were joined on the call by Randy Karg and Chris McMahon, also on the Development Committee. you, as I think you know, we issued our RFP at the beginning of April. There's a 120-day response time, so we're very interested to see what we'll get and how we'll be able to work with various ideas going forward. I just really had two questions, and I'm going to ask them both at the same time. The first is around upfront costs. It was mentioned that one of the obstacles of the system is upfront cost or infrastructure cost. And so, we have a project with really no or very little workable infrastructure, and the town has expressed a reluctance to pay the cost of that infrastructure and wants to see the developer carry that cost as part of their proposal. So question one is, in your research, did you come across any financial programs or incentives, maybe at the state or federal level, that might be available to a developer to help address upfront costs for this project? And then the second question relates to the windows. I've worked on a number of historic buildings over the years, and it is amazing to me how long it takes developers to get their windows approved by the Park Service, a matter of years in some cases. And so I'm curious to know whether the Park Service, whether passive house, windows meeting a passive house standard have already been approved in other projects by the Park Service, if that's come up at all.
I can answer the second question easily, which is yes. The Zola's windows have been approved by the Park Service and other agencies and have been used, and those are all passive house certified. Things are so much more available now than they were even just 2 years ago. The kind of availability of these mostly European designed windows they're now manufacturing them here. It's pretty remarkable how fast that's changed. And so that's the window thing. I'd say is a former problem, which is now not a problem. It really, at least it's certainly in the case of Zola's windows, those ones I know have been approved by the Park Service. The other question about incentives, I would say unless someone else in the team looked without telling me about it, I don't think we looked for incentives. We did look at ownership and management models. So the idea should be that this should be a profitable enterprise for someone can make an investment with a long enough horizon that they can actually make a profit by managing a district energy system. And that exists in almost every place. So Boston has a company that manages their district energy systems. And we found one example, the Lulu Island District Energy Management Company in Canada, that they manage a district energy system. So they were created by the city, but then they operate as a for-profit company and manage and invest in the DES systems. It did require an ordinance to bring them into being and to enable that type of management system. So that I think is more where we ended up looking was how can for-profit companies manage and own the DES systems.
Thank you.
Yeah, so Ben, it sounds like the couple of models there are essentially a municipal utility, just like you'd form a municipal electric company, only this is a municipal district energy system, if that were something Medfield could consider. But then sort of a commercial party that the prime contractor might subcontract the district energy, building operation and management to that other party, and there'd probably be some almost like a power purchase agreement in solar, but a heating purchase agreement between the developer and the subcontractor for the DE system. Am I getting that right?
Yeah, it can be. It can simply be a contract that says, the system managed and owned by this utility, and it can be a private entity or it could be a municipal entity. What I saw is that there are a number of these companies that manage that essentially do this both here in the US, more of them in Canada, and also in various European countries. And they look at these projects as investments. And so the question is how to make it an appealing prospect for them. But again, there may well be utility incentives. I'm sorry that was it Penny that disappeared, because this would probably be her area.
Well, and I would also expect, Ben, as the state figures out how to implement the climate bill, I suspect we'll see some incentives developing, and there'll certainly be a couple of years while the state figures that out, but we've got a couple of years by the time we pick a developer, they go through financing and design and things like that. So with any luck, those things will come together.
I'll just jump in if I can, Jim, on the question that Todd broached of, which is a broad question of what possible incentives might say, which is a good question. And I know Kelly just dropped off the call also because she might be a source at the state level to address. There are significant incentives right now for heat pumps, for photovoltaics, for passive house construction for multifamily at least. I don't know quite how they map onto a massive project like this. But I think there are answers out there, Todd, to the very good question you're bringing up.
I don't know if anyone has any
final questions. Exactly.
Yeah, questions or comments, and obviously we can answer some of these afterwards, or kind of be in correspondence with you.
How do we get this?
Sorry, Fred, your connection's a little bit in and out.
I'm sorry. I just made a whole speech about incentives. I hope at least half of that got.
Oh, we got that.
Through. But then I was following. Okay, good. Then I was following up with a quip, and maybe this is a way to end the meeting. I don't know. But your students, Ben, they were all terrific. I'm giving 2 thumbs up.
Totally.
I can only second that, and thank you, everyone. That was a really awesome and very informative interpretation discussion of this topic. And I want to just add that, I think just visualizing what a district energy system would look like would be highly compatible with the historical nature of not having decentralized air source heat pumps installed outside every building, or AC units, or, just really removing all signs of infrastructure and just maintaining the campus in its pristine condition would be really such an asset. So thank